Okie doke. So we're going to start talking about applications of derivatives in this little video here. And so we're going to start with some key vocabulary and go through this whole thing. And this looks a little scary, so don't panic. I'm going to go through it kind of quick and just give you the main points of it, right? So what we're essentially talking about vocabulary-wise is position, displacement, velocity, and acceleration, all right? So if you were going to talk about position and you were thinking about a particle moving, right? Like a position, let's just say a particle was floating around in space and went around like that. The position would be where that particle lives in that moment. That's its like location, right? So position is location. Displacement, I don't know if you remember like from physics, water measuring like water displacement, but it's a measure of change of location. So you went from, let's just say a height of 100. So let's say that was your position. And then you went to a height of 60. So your displacement would be 40, right? Because your displacement is how your position changes. So these two words really go along well together. Velocity is how fast this thing is occurring. So let's just say you went from 100 miles an hour to 60 miles an hour, or you went from a height of 100 to a height of 60. How fast did that happen? Did that happen in 10 seconds the way it's shown here, or did that happen in 1 second? Because dropping 40 feet in height or dropping 40 miles an hour, I'll add that in there. So sorry, 40 miles, decreasing your speed by 40 miles. If that happens in 1 hour versus 1 minute versus 30 minutes, right? Those are all different speeds. So your velocity is the speed, it's the rate of the displacement. It's how fast things are changing over time. And acceleration is how fast velocity is changing. So are you speeding up or are you decreasing your speed? Things like that, all right? So let's go through a couple of these things so that you can see it in the calc way. And this is, again, what we're talking about. The idea that the derivative gives us a way to discuss how any of these quantities are changing, usually with respect to time at any given moment. So how fast is the position changing over time? So in calc, we're going to talk about position functions, and that's noted usually with these statements. So hopefully you can figure out that the letters in here, all T's, represent time. So your function at time t, like that's your position. It also has P for position. X and Y are just like the X and Y axis. So what would your position be here versus what's your position here? So that's why we use those letters, and it's just T's for time, right? Okay, and then we've got our velocity. And so our velocity is going to use V of t, velocity at a certain time. But the way that we find velocity is by using the derivative. So if you take any of these equations and derive them, take their derivative, you are now looking at the velocity. Okay, and now this is the fun part. This is the acceleration. The acceleration is the double derivative. It's the derivative of velocity, or take the derivative twice from the original function. It's going to make a lot more sense once I do an example, so don't freak out and panic. And then speed is just the absolute value of the magnitude, but we're not going to do any of those functions. So we're going to skip sort of the idea of speed. All right. So you can read through the rest of it. I mean, I just really tried to give you a quick little version of this. I'm trying not to make the video too long, but I think it's going to get a little long in terms of once we start doing the application, right? Distance obviously is how far something traveled. Displacement, again, is the change. So if you went from 30 miles away from your house to 70 miles away from your house, you traveled, 100 miles total because you traveled from 0 to 30 and then from 30 to 70. But the displacement would be the 40 and things like that. Again, I think it's going to make a lot more sense once we do an example. Okay. You've got a particle moving along a horizontal line so that its position at any time t greater than 0. That just means we're talking about time going into the future, not in the past. That's why it's not negative, and is given by that function. Okay, all that means is that there's this atom in space moving around and doing weird things like this. And this equation here maps its location in time. And so hopefully you already know that an equation that has t squared in it is a parabola. So essentially this shape looks something like this. It's traveling along this pathway. Oops, just kidding. It's traveling along this pathway. It's not upside down. You don't really need to know that. But what you do know then, you need to know how to do, is figuring out the words that kind of are going with that. Okay. So find the displacement of the particle during the first 3 seconds. So what's displacement? Displacement is where a particle starts, where a particle ends, and the gap in the height is displacement. So I need to know where the particle was initially, and then I need to know where the particle was finally, and then the gap between them, that's displacement. So displacement, I'm just using this equation. That x of t, all the functions are going to be position functions right off the bat, right? So how do I figure out, and it says here like during the first 3 seconds. So during the first 3 seconds means I think initially the time that we have is 0 seconds. So the starting point started at a time of 0 seconds. That's really all you have to figure out first is what time do you want me to start with? And since it says during the first 3 seconds, I'm thinking it starts at 0 seconds, and I think the final time is 3 seconds. So hopefully that makes sense. So if I need to find the displacement during the first 3 seconds, I need to find the height at 0 seconds, the starting height, and then I need to find the final height or final position. I shouldn't say height because we're talking about the x-axis, but whatever. We go to 3 seconds. So now the question is, all right, how do I find where this particle lives at 0 seconds? And since 0 is a measure of time and that stands in for this, essentially all we're going to do to find the initial position is sub in 0 into the equation. So if I substitute 0 in for t, because again, t stands for time, 0 squared is 0, 4 times 0 is 0, and that's 3. So what this is telling me is that at 0 seconds, the particle was 3 something. Technically, it says here 3 feet away, or around 3 feet. So now I have to figure out, well, where did that particle go to after 3 seconds? The particle moved somewhere. Where did it go to? So now I'm going to sub in 3 into the equation. So 3 squared minus 4 by 3 plus 3. And then we'll go here. So 3 squared is 9. 4 times 3 is 12. 9 minus 12 is negative 3. Negative 3 plus 3 is 0. And so it started at 3, and then it went to 0. So now the displacement is the gap between the two. So that would be 3. And you can just do 3 minus 0, things like that. Or technically 0 minus 3, but again, the gap isn't positive or negative, so the number should always kind of be positive. It's fine there. At least for what we're doing. It's not 100% accurate right there, but... So, okay. If I said to you, find the displacement from the 4th minute to the 8th, sorry, not 8th minute, I'm going to use seconds because that's what the example is. So if I said, I wonder how much change occurred between 4 seconds and 8 seconds, where did that particle live at 4 seconds? And where does it live at 8 seconds? And then let's find the gap in that distance. So if that was the case, all I would do is I would go to the equation and sub in 4. So 4 squared minus 4 by 4 plus 3. 16 minus 16, 0, so that would be 3. I would say, okay, the particle at 4 seconds lives at 3. Where's the particle at 8 seconds? Sub it in. 8 squared minus 4 by 8 plus 3. So 64 minus 32. Is that right? 8 squared, 64. 64 minus 32 is 32. Plus 3 is 35. And I would say, okay, at 4 seconds, the particle was at 3. At 8 seconds, the particle was at 35. So the displacement between the two would be 32. And that would be my final answer. So displacement is measured by finding the position of the initial time, the final time, and then finding the gap in the distance. So how you find the gap in the distance is you sub in the initial time into the equation, you sub in the final time into the equation, and then you subtract the final outcomes of each of those. Okay? So I hope that makes sense, because now we're moving on to velocity. Okay. Velocity is asking me about the derivative. So all velocity is always going to be the derivative of the original function. So as soon as I see the word instantaneous velocity, instantaneous means at that moment, not finding how fast this is changing. If we go back to that very first example I did in class, and when we drove like 200 miles to Wisconsin, 200 miles in 2 hours, right? If the rate of that would be, well, yes, I'm driving 100 miles per hour, but that's not the instantaneous rate. That's the average, because I wasn't going 200 miles an hour, 100 miles per hour the entire time, right? Like I was slowing down, I was speeding up. This is an average. The instantaneous, that's why we need derivatives, right? So first thing I'm going to do when I see instantaneous velocity is take the derivative of that equation. So I'm just going to copy the equation here just so that we can be very clear on what's happening. You can zoom in. So now I'm going to take the derivative, and that's the shortcut equation for, the prime there, that little dash there means I'm taking the derivative of this. So the derivative of t squared is 2 times 1, which is 2, t, decrease this by 1. So technically I'm going to write there just to make it obvious. Do the same thing here. There's a 1 there. 1 times -4 is -4. T, drop the degree, 0. The derivative of a constant is nothing. And so I'm going to clean that up a little bit and remind myself that 2t to the first is 2 and t to the 0 is nothing. And so the derivative of the equation is this. Okay, but remember, if I said find the instantaneous velocity, remember velocity means speed. So if I said how fast were you speeding when you were 3 hours from your house? I know it says seconds here, but let's just pretend you were talking about 3 hours. How fast were you going after you were gone for 3 hours? Probably not the same speed at the first hour. Probably not the same speed as you were after minute 1, right? So if I said, well, how fast were you going? You're not going to say, well, I was going 2t minus 4 miles per hour. That doesn't make any sense. So somehow we have to use this number here, and hopefully it makes sense. We're just going to sub it in. So we're going to take that 3, and I'm using a lot of proper notation here. So we're replacing that t with 3, because again, t stands for time, and we know the time, it's 3. So we sub in 3 to our velocity equation, which is this one. 6 minus 4 is 2, and so the instantaneous velocity at 3 seconds is 2. Okay? So to find displacement, we're going to sub in some numbers. It's got to always be 2. Remember, displacement is a gap, so you need a first and a second. Velocity is going to take the derivative of this and get you an equation that you're going to use. And then acceleration is the exact same thing, except you're taking the derivative one more time. You are now taking the derivative of your velocity equation. So the derivative of your velocity equation was this. So the acceleration equation, and I'm going to do 2 dots there. And the reason I'm doing 2 is because we found the derivative once to get velocity and a second time. So we started with x. X prime got us to velocity. X double prime twice is going to get us to acceleration. So really you just have to think about taking the derivative of this equation again. So the derivative of 2t to the first, 1 times 2 is 2. T to the 0 is nothing. And the derivative of constant is this. So I actually don't need this at all, because x double prime of t is just 2, and there's your final answer. So acceleration is the derivative twice. If your equation did have letters in it, like if this was 2t squared and this was 4t or something like that, then yes, you would need to sub that number in. But since there's nothing to substitute, there's no t, we got that. Okay? All right. So hopefully that makes sense. Displacement, you use the original equation, plug some things in, get a gap. Velocity means take your equation and find the derivative and use that derivative with a number. And acceleration is do the derivative again to this and get a new equation that you can substitute a number in if you have a letter there. If you don't, you don't. Okay? Okay, I hope that helps, and I hope you're not totally panicked. If not, we'll figure it out when I come back. All right?